mencapai misi yang satu, permisi kita bantu.
Tahniah. Siaran langsung ini dibawakan khas kepada anda oleh Akademi YouTuber Malaysia. Tumpukan perhatian anda. Siaran langsung akan bermula sebentar lagi. Link sijil akan diberikan di hujung siaran ini. Pastikan diisi dalam tempoh yang ditetapkan. Terima kasih.
Assalamualaikum. Good evening and hi to all teachers, parents and the wonderful students. So welcome to Pusat Tuisyen Academy YouTuber, a joint venture with eDidik Malaysia and Kelab Guru Malaysia with the hashtag Bermula Percuma Selamanya Percuma, initially free and forever free. So before we proceed, let's begin our session with the recitation of Kitab Al-Fatihah. And for the non-Muslim, please take a moment of silence. Okay, so how is everyone doing today? My prayer is that everyone is in the best of health and ready to proceed with today's class. So let me introduce myself. I am Madam Rosmaya from SMJK Yuhua, Kajang, Selangor. And today I will present alone. So before we start our discussion today, so please subscribe to my channel so that you won't miss any of my new video in the future. And as usual, the lesson will last approximately 1 hour and the certificate link will be given at the end of this lesson. So you can only use eDidik email or MOE email to claim the certificate. So I will put the link to apply the eDidik email in the chat box now. Okay, paste it. Okay, so posted already. Okay, so be sure to follow the class up until the end and give your full cooperation in making this lesson a lively one. I would also like to remind students to use appropriate language if you wish to post comments in the chat box. I'm pretty sure all of the students here are excellent students who will uphold a positive classroom environment. So stay focused, and if you have any questions, please write in the chat box. Okay, so now I'm going to open my slide. Okay, so let me introduce the pre-U teams that we have in the Academy YouTuber. Okay, so we have altogether 5 teams, pre-U teams. So this is a physics pre-U team. Okay, the physics pre-U team is led by me. Okay, I'm Madam Rosmaya, and the three other members are Teacher Su, Teacher Absayu, and Teacher Non. Okay, for maths team, it is led by Teacher Im. Biology pre-U team is led by Cikgu Faiza. And chemistry pre-U team is led by Cikgu Shahnun. And we also have Perakaunan and Economy pre-U team led by Madam Fizi. Okay, Academy YouTuber also has apps where you can download it from Google Play Store. There are a lot of videos there, including the physics video. Okay, so now we have come to the main objective for today's live class. What is our learning objective for today? So we are going to do revision on chapter 10 and chapter 11. So chapter 10 is the topic is thermodynamics of gases, and chapter 11 topic is heat transfer. So the link question PDF I also posted already yesterday in the description part, and also in the chat box. You can get from the chat box if you just enter for today's live class. Okay, so this is the first question. So let us read the question first. So 2 moles of an ideal gas in a cylinder have a volume of 5 times 10 to the power of negative 2 meter cube at a temperature of 300 Kelvin and a pressure 1 times 10 to the power of 5 Pascal. So the gas undergoes the following process. Okay, number one, isobaric expansion to twice its volume, then followed by second, cooling to its initial temperature at 300 Kelvin at constant volume, and finally, okay, third step, isothermal compressions back to its initial volume and pressure. So there are 4 questions. The first question, draw a PV graph to show the 3 processes stated above. Label clearly the processes. Oh, I can read there, Cikgu Sufi. Thank you for dropping by. Okay. Thank you for the uh, wish. Okay. Then we continue with the read the question first. The second question say what is the temperature of the gas at the end of process 1, and then the third question find the pressure of the gas at the end of process 2, and then question 4 find the network done by the gas in a complete cycle. So we do question 1 first. Okay, draw a PV graph. To draw a PV graph, okay, so that's mean we plot the y-axis and x-axis, okay, P against V. Don't forget to put the unit, the unit given is Pascal for pressure and the volume meter cube, and the origin label also with 0, okay, at the origin. Okay, for the first step, isobaric, so it's a constant pressure. Isobaric means constant pressure. So you draw a straight line. It must be horizontal, horizontal line. And don't forget to show the arrow, okay, because it's expansion, okay, expansion. So show the arrow and label with the pressure and volume given. Okay, so 5 times 10 to the power of negative 2, this is volume, first volume, and the pressure, first pressure, 1 times 10 to the power of 5 Pascal. Okay, then it become twice of its volume. So you label also down here at the x-axis, 10 times 10 to the power of negative 2 meter cube. Okay, then this is draw the line for the second process. Second process, so label with 2. So it's cooling to its initial temperature of 300 Kelvin at constant volume. So constant volume, that's why you must draw a straight line. Okay, no changes in volume. And finally, the third process is isothermal compression. So you draw a isotherm. Okay, you draw isotherm. So it's a curve going back to its initial volume and pressure. Initial volume is 5 times 10 to the power of negative 2 meter cube, and the initial pressure 1 times 10 to the power of 5 Pascal. So go back here. Don't forget to also to write to draw the arrow. Okay, back here compression, compression. So the arrow is this way. Okay, now we have draw the PV graph complete. So you get full marks for drawn like this together with the label. So be careful, label is very important. So one of the mark is the label. Okay, next question is what is the temperature of the gas at the end of process 1? So which is process 1? So there is process 1. So we take a look at what is given in the data or information given in the question. So we have a number of moles, we have temperature. This is initial temperature, and we name as T1, then initial volume, then initial pressure. Okay, so final volume will be 10 times 10 to the power of negative 2 because the expansion become twice, okay, twice of its volume. So 5 becomes 10 times 10 to the power of negative 2 meter cube. Okay, so these are all data given, information given in the question. So from the given data, so that's mean we can use the formula PV equals to nRT. Okay, so P we need to use here because this is the question asks the end process the first process. So that's mean we need to use P1 information from the graph is P1 and V2. Be careful with the P and V you are going to substitute into. Okay, so substitute P1 and this V2 into the question. So N is number of moles and R is the molar gas constant and T is the temperature that we want to find in the question. So you substitute P1 and volume 2 into the equation and number of moles, 2 moles there, and R is 8.31. So we calculate, we get T equals to 602 Kelvin. So that is question number 2. T, we got, the answer is T equals to 602 Kelvin. Okay, done for question 2. Next, we continue with question 3. Okay, question 3, find the pressure of the gas at the end of process 2. Okay, so where is process 2? We've drawn just now the graph. Okay, so this is the process 2. Okay, at the end process, so that's mean the point is here, and the temperature for this, there are two isotherm here. This now we calculate 602 Kelvin. So be careful with the temperature. So the temperature for this isotherm is 300 Kelvin. So we are going to use this temperature, not this temperature in our next substitution of value. So for PV equals to nRT, again we use equation PV equals to nRT. So the T that we are going to substitute here is this 300 Kelvin, not 602 Kelvin. So this is where the student make common mistake student make. So which temperature to be put? Okay, so now for the pressure of the gas at end of process 2. So that's mean the P2, here we're going to find P2, and the volume for this point is 10 times 10 to the power of negative 2 meter cube. So we substitute this both into there. 300 Kelvin, P2 is what we're going to find, and then the volume. So be careful with the information given. Okay, now we solve for P2, we get 4.99 times 10 to the power of 4 Pascal. Okay, so remember to write in 3 significant figures because given here is 3 significant figures. The data given is 3 significant figures. Okay, done for question 3. Next, we go to question 4. Okay, question 4. Find the net work done by the gas in a complete cycle. Okay. So the net work done, that's mean we are going to total up all the work in all the process. So we have process 1 followed by process 2 and followed by process 3. So work done in process 1 plus work done in process 2 and plus the work done in process 3. Okay, so or if in the graph, the area work done is represented by the graph is the area label or sketch here. Okay, this is the area where we're going. If you can calculate the area, but we cannot use calculate the area here because this is a curve graph. So instead, how to get this area for the net work done? So we use formula for each of the process. So for process 1, the formula is we use pressure times change in volume. Because it's a horizontal line, so it's constant pressure. So we can use this formula. Okay, so pressure is 1 times 10 to the power of 5. So the changes in volume will be 10 times 10 times 10 to the power of negative 2 meter cube minus 5 times 10 to the power of negative 2 meter cube. Okay, so this is the change in volume. So we get the answer 5 times 10 cube joule. So this is for work in process 1. So you substitute into the equation. Next is work done in process 2. So work done in process 2, the volume is constant. So it is understood that there is no work done. Automatically in your mind, when there is no changes in volume, so that's mean the work is automatically zero, no work done. So you substitute there zero. So no need to write down the zero also can. I just show it here so that you remember that when the work when there the no changes in volume, automatically in your mind the work is zero. Okay. Now for the process 3. So for process 3 is it is a isothermic process. So we use the formula for the work done. For isothermic process, it is nRT ln VF over VI. VF is the final volume divided by initial volume. So this is the formula for the formula of work for the isothermal process. Okay, so you substitute the N, R, molar gas constant, and then the temperature. Be careful. Okay, don't substitute this temperature because it's in we are going to find the work for process 3. It's isothermal process 3. So you substitute 300 Kelvin. Okay, so for the V is final over initial. So be careful also which one is final volume and which one is the initial volume. So final volume is 5 times 10 to the power of negative 2 meter cube, and initial volume 10 times 10 to the power of negative 2 because look at the arrow here, this is compression. So you know from the compression or the arrow here, so you know which one is the final volume and which one is the initial volume. So be careful with all the values that you substitute into the equation. Okay, so to solve, we get negative. We get negative. So negative 3.456 times 10 to the power of 3 joule. Okay, it is logic to get negative because this is compression. Okay, so we substitute into all here. We total up all the work done that we have calculated. So the answer will be 1.54 times 10 cube joule. Okay, so this is the work done. Okay, we put there. Okay, now remember that for all the process, isobaric, isochoric, there are 4 processes you need to memorize. Isobaric process, isochoric or isovolumetric. There's a typing error there. Yes, correct. Isovolumetric, isothermic, and adiabatic process. So these are all the what we've discussed in the this topic, the thermodynamic topic. So you must know how to distinguish between all the process, thermodynamic process. Okay, for the isobaric process, it's a constant pressure. So the formula for work is P, change in volume. And the Q, the heat absorbed or heat supplied equals to NCV delta T. This is from first law of thermodynamic. Q equals to delta U plus work done. Delta U is internal energy. For V constant, the work automatically in your mind will be zero. And the Q heat is equals to the internal energy because the work zero. So from first law of thermodynamic, Q equals to the internal energy. When you substitute zero into here, so you get Q equals to internal energy. Change in internal energy. Okay, then for the T constant, so the change in internal energy will be zero. So when you substitute into the first law of thermodynamic, so you will get that the Q equals to the work done. And for the adiabatic process, nothing is constant. P, V, T all change. So that's mean the Q, the Q is zero. For special, for adiabatic change or adiabatic process, the Q is zero. No heat is allowed to enter or to leave the system. So Q zero. So when you substitute into the first law of thermodynamic here, so you get internal energy equals to negative work done. And also we derive the work done is equals to the negative molar gas capacity, molar heat capacity at constant volume over R. Bracket P2V2 minus P1V1. Or you can use relationship to gamma, so 1 over 1 minus gamma, bracket P2V2 minus P1V1. So there are a lot of formula for work done, so you just memorize one or two only, because the rest you can relate with the values, the gamma, like the CV or CPM, and so on. PV equals to nRT, also you can relate with that equation. Okay, so this is what we have discussed in topic thermodynamics. Okay, next we go to question 2. Question 2 about it's more on molar heat. Molar heat capacity. Then we read the question together. Okay, 4 moles of an ideal gas is cooled down at constant volume from 610 Kelvin to 550 Kelvin. A total of 5006.4 joule of heat energy is removed from the gas, and relative molecular mass of the gas is given is 32. Okay, so question A, state if work is done on the gas and then give a reason. And then B, find the molar heat capacity at constant volume. Question 2, hence calculate the molar heat capacity at constant pressure. C, determine the specific heat capacity at constant pressure. And D, calculate the change in internal energy of the gas. Okay, so we process the question first, what is given in the question. You are given a number of moles, you are given temperature, this is T1, and T2 will be 550 Kelvin, and the heat energy is 5006.4 joule. Okay, so state work is done or not. Then you check constant volume. That's the keyword. So that means no work is done on the gas. Remember that if constant volume, so that means no work is done on the gas. So give a reason. So this is the reason. Because the volume of the gas remains constant. Okay, now we go to question B. Find the molar heat capacity at constant volume. So molar heat capacity is CVM. The symbol we use is CVM at constant volume. So you are given Q. So you can use formula Q equals to N CVM delta T, or change in temperature. So you are given temperature. Okay, and CVM is what we're going to find, and then Q also given. So you can use this formula. And be careful with the sign. Q is negative. Okay, so because the gas is removed, the heat energy is removed. Heat energy is removed. So that's mean what you must label it with negative. Okay, N is 4 moles, and then CVM. Change in temperature, final minus initial. So 550 minus 610 Kelvin. So change in temperature, be careful, final minus initial. So you will get CVM equals to, you rearrange the equation and you get 20.86 joule per mole per Kelvin. So this is molar heat capacity at constant volume. Okay, next we go to question 2. If you got any problem, you can write there in the chat box. I can see whatever you write there in the chat box. Okay, so now we go to question 2. Okay, question 2. Hence, calculate the molar heat capacity at constant pressure. So molar heat capacity at constant pressure we label as CPM. So P stand for pressure and M stand for mass. So molar heat capacity at constant pressure. Because we have calculated CVM, so we can use the relationship CPM and CVM with molar gas constant R. So we can use this formula, CPM minus CVM equals to R. So we substitute CVM 20.86, then R is 8.31, then you get CPM equals to 29.17 joule per mole per Kelvin. Okay, very simple. Okay, next is, this is the answer we write there. Okay, now for question C, determine the specific heat capacity at constant pressure. So be careful with the capacity, there are many three kinds of heat capacity. This is specific heat capacity. The one that we calculate for B is molar heat capacity. Okay, now we are going to find specific heat capacity. So that's mean is in the if the unit is a joule per kilogram per Kelvin. So it means the heat how much heat is absorbed to rise the 1 kilogram of energy. Okay, 1 kilogram of the energy to rise it in 1 Kelvin. Okay, so that is the specific heat capacity. Okay, so the symbol we use is small letter C. Okay, small letter C for specific heat capacity. Okay, C is equals to the heat capacity per M for the specific heat capacity, because it is related to the mass. So heat capacity over mass. If in terms of unit, so it's joule per kilogram per Kelvin. It's not mole. So joule per kilogram per Kelvin. We can, because we calculate CPM in B, so you can use CPM equals to C over N. Okay, heat capacity, because heat capacity is joule per Kelvin, so divided by a number of mole, so this is mole. Okay, so you can use CPM, the relationship between CPM and the heat capacity and number of moles. Okay, now we combine these two. So heat capacity is C times M. You substitute into the second equation, so you get Cm over and then number of mole is M mass of the gas divided by the molar mass. Okay, this one is for the number of moles. So number of moles, there are two equations you need to memorize. Mass of the gas divided by molar mass, or number of molecules of gas divided by Avogadro number. So there are two formula. So you choose this one because we are going to use CPM. Okay, so you cancel M and you get heat capacity is equals to the CPM divided by M. Okay, so now you substitute CPM and then the molar gas constant or relative molecular mass of the gas or molar gas constant. So you substitute into here, but be careful, this 32 is in gram per mole. Okay, so you need to convert to kilogram because 32 is in gram per mole. So 1 mole contain is 32 gram. So that's mean 32 times 10 to the power of negative 3 kilogram. Okay, convert to SI unit. So be careful. This is the unit is where the student make careless mistake. Common careless mistake is with the unit. Okay, so the answer is 911.6 joule per kilogram per Kelvin. So this is the specific heat capacity. Okay, at constant pressure. So here given at constant pressure, that's why we use CPM. We don't use CVM. We use CPM because the questions want specific heat capacity at constant pressure. So this is another reason why we use CPM into here. Okay, so done for C. Okay, now we go to D. Okay, so we go to D. Calculate the change in the internal energy of the gas. So change in internal energy of the gas is delta U. Okay, the symbol we use is delta U. Delta means change in. So we can use first law of thermodynamics. So Q equals to delta U plus work done. So yeah, there are many law of thermodynamics, but in physics we learn one only, first law of thermodynamics. Okay, so we substitute Q, negative 5006.4 joule. So delta U is what we're going to find, and the work done is 0 because it's constant volume. So we get internal energy is equals to negative 5006.4 joule. And it's logic to be negative because the volume here, temperature, because the temperature decreases. You can see here temperature decreases, so it's logic to be negative. Sometimes you think the logic can help you a lot to avoid careless mistake in the sign, especially sign. So to get negative is logic because the temperature decreases to 550 Kelvin from 6010 Kelvin. So it's logic to be negative. Okay, so that's mean internal energy decreasing. Okay, if the question asks to reason your answer, so that's mean the internal energy is decreasing because negative. Okay, now we go to question 3. There are altogether 3 questions on thermodynamic chapter 10. Okay, so a gas has a value of gamma equals to 5 over 3. So find the degrees of freedom for the gas and determine whether the gas is monoatomic, diatomic or polyatomic, and then determine the molar heat capacity at constant volume CVM and the molar heat capacity at constant pressure CPM. Okay, so now you are only given gamma, so you need to understand what is gamma. So gamma is a ratio of CPM to CPM, CPM to CVM, okay, molar heat constant at constant pressure and molar heat capacity at constant volume. So you need to understand what is the meaning of gamma. Okay, so to degrees of freedom, you need to know the relationship between gamma and degree of freedom. Okay. Formula is gamma equals to F plus 2 per F. F is degree of freedom. Okay, how to get this? You also must know another formula for gamma, okay, which is ratio of CPM to CBM. So CPM is equals to half bracket F plus 2R, and CVM, okay, molar heat capacity at constant volume is half FR. So that's why you get F plus 2 over F. Okay, so now you substitute the gamma 5 over 3 equals to F plus 2 per F. Then you solve for F, you get F equals to 3. Okay, so that's the answer, F3. Okay, now to determine whether the gas monoatomic, diatomic or polyatomic. So from the number of degree of freedom, so 3 means it is monoatomic. If it is 5, diatomic, and if it's 6, it is polyatomic. So memorize that. Okay, so next question is molar heat capacity at constant volume. So you need to use the formula related to F. Okay, so that means CVM here equals to half FR. So you substitute 3 into here and R is 8.31 and you get 12.47 joule per mole per Kelvin. And lastly is molar heat capacity at constant pressure, CPM. So for CPM, you use a half bracket F plus 2 times R. So F is 3, so substitute into the equation here, 3 plus 2, 5 times 8.31 divided by 2, so you get 20.78 joule per mole per Kelvin. Okay, very simple the answer. You just need to memorize the formulas because in the exam, formulas not given. Okay, so now that's question 3. And also actually you can use formula CPM minus CVM equals to R. This one we've used in the previous question, question 2. So you can also use CPM minus CVM equals to R. So because you have calculated in C1 CVM, so that means CPM minus 12.47 equals to 8.37 and you get CPM 20.78 joule per mole per Kelvin. And do you realize that we get same answer? Okay. So no matter which equations you use, you still get same answer. Okay, so this is all the formula in the thermodynamics topic. Okay, you need to memorize. Okay, from the first law of thermodynamics, the relationship between CPM and CVM with R, and then from here we continue derive the gamma, which is the ratio CPM to CVM. The formula of CPM relate to the degree of freedom. Okay, and then from the definition of work, we didn't put negative there, so that's mean we get work for work done on the gas will be negative and work done by the gas will be positive, because initially we define the work is this one. Okay, so now I think we have already live for 34 minutes, so we take a rest, okay, for the iklan. Okay, after 1 minute, advertisement for 1 minute.
Tuisyen online percuma. Tuisyen online percuma. Layari www.academyyoutuber bagi mengikuti tuisyen online secara percuma. Prasekolah, sekolah rendah, sekolah menengah, semua ada di Akademi YouTuber. Rujuk jadual di laman sesawang www.academyyoutuber.com. Semoga masa terluang anak-anak anda diisi dengan sebaiknya. Tuisyen online percuma, mestilah Akademi YouTuber.
Okay, welcome back everyone. Okay, for the next 3 questions, okay, I have given this question earlier. There are altogether 6 questions. So the next 3 questions will be on next topic, which is heat transfer. Okay, so let's us read the question. So question 4. Okay, 2 rods, a copper and aluminium, okay, of equal length and cross-sectional area are joined together and perfectly insulated as shown in the diagram below. Okay, the temperature at the open ends of the copper and aluminium are 80 degrees Celsius and 30 degrees Celsius respectively. Okay, the thermal conductivity of the copper and aluminium are 401 watt per meter per degree Celsius and 235 watt per meter per degree Celsius respectively. So the question is, describe heat transfer mechanism in the copper rod and calculate the temperature at the interface of the 2 rods. So for description, that's mean you need to give the process, the process, okay, for question that which come up with the words described here. So usually this is 3 or 4 marks, okay, so you need to explain the process. So at the hot end here, starting 80 degrees Celsius, okay, the free electrons have a higher kinetic energy. So this is one point. Okay, the second point, okay, so now movement of electrons from the region of higher temperature to a region of lower temperature, okay, causes the transfer of heat from the region of higher temperature to the region of lower temperature. So you mentioned about the movement of electrons, the free electrons just now, which has a higher kinetic energy. So this is the heat started to transfer already, the process of transfer of heat. Okay, then the last point will be at the hot end the atoms will vibrate. See, this is another method of transfer of heat, which is from vibration. So at the hot end, the atoms will vibrate faster. So the atoms with higher vibration will cause the nearby atoms to vibrate faster. So this cause of heat transfer. So the key point here is you mentioned the flow of heat transfer from hot end to lower temperature, hot end to cold end. Okay, that is the first point. The second and third point, you mentioned the 2 methods of heat transfer. The first one is by the collision of electrons or movement of electrons. And the second one is with the vibration of the lattice of the atoms here. So the atoms vibrate faster. This is from vibration method. Then you get full marks. Okay, next question 2. So question 2, calculate the temperature at the interface of the 2 rods. Okay, so to calculate the temperature at the interface, that means we are going to calculate temperature in between here. Let's name it as theta. So this is the first at hot end that we name as theta 1, and final end will be final temperature at final end will be theta 2. Okay, this is cold end. And the thermal conductivity, so we use K label cuprum and K label aluminium for thermal conductivity of aluminium. Okay, so now we use the formula of the rate of heat flow, which is dq by dt. Okay, this is rate of heat flow equals to negative Ka theta by dx, which is K is thermal conductivity, A is a cross-sectional area, and d theta is the change in temperature, and X is the distance, the length of the combination of copper and aluminium, or copper or aluminium. Okay, so another key point here is at steady at steady state, this is insulator, right? So that's mean at steady state, the dq by dt, or rate of heat flow, will be the same. Rate of heat flow will be the same. So dq by dt for cuprum is equals to dq by dt for aluminium. So you equate them, then you substitute the k value for cuprum. Cross-sectional area not given, but they will be the same. Okay, they are same size. Cross-sectional areas same size. And then temperature, be careful, is final minus initial. So final will be theta. So theta minus 80 degrees. Okay, theta minus 80 degrees. The heat flow from here to here, so that's mean theta minus 80 degrees. The negative cancel out already, so no need to put the negative. And divided by time taken. So time taken will be the same. Okay, for the this is aluminium. For aluminium, so 235 cross-sectional area and time will be the same. So final for aluminium, final temperature will be 30. So 30 minus theta. So you must be very careful with the temperature substituted into, which is final minus initial. And the left side for aluminium also final minus initial. So if not, you won't get the answer. Be careful with the sign used for temperature, and also here negative sign. Okay, negative here cancel out, and then A and T also cancel out because equal length and cross-sectional area. Equal length and cross-sectional area. Okay, this one I label wrongly. It's supposed to be X, not T. T is for time. Just now I mentioned T as time because I label it with T. So be careful in the exam. So this is also common mistakes made by students. You look at what I did. I use time here. This is where common mistakes student make. So this is supposed to be X, length, which is equal length. So you cancel the length. Okay. I repeat again. This one is not T. This one is X, distance or the length. You can label with X or you can label it with L. Okay. So I hope you don't make mistake like I did for this label, T. Okay. Now we solve. We get theta equals to 61.5 degrees Celsius. Okay. So that's the answer. Okay, I hope you all can understand. Okay. Next, we go to question 5. Question 4 got 2, A and B. So still question 4B. Okay, most of the question we discuss here is more on essay part, section C part. Okay, so question B. For B, an isolated object with a surface area of 3 meters squared, temperature of 25 degrees Celsius, and emissivity of 0.80 is placed in an environment of 75 degrees Celsius for 50.0 seconds. So state the factors which affect the amount of energy radiated by the object. Okay, determine the net rate of energy exchange of the object. And 3, determine the net energy absorbed by the object. Okay, so for the factors, it's very easy. You refer to the formula. So from the formula, you see that the factor are temperature, surface area, and nature or type of the surface. Okay, this one we get from this formula. P equals to E. E is emissivity. Okay, sigma here, last symbol sigma here is for Boltzmann constant. A is surface area. Okay, surface area. T is temperature, and E and the E is depends on the nature or type of the surface. And P is the power radiated. Power radiated, or rate of amount of energy radiated or power radiated. So that's mean if rate of energy radiated will be dq by dt. P is equals to dq by dt. Okay, so now we are going to use this formula to determine the net rate of energy exchange of the object. So that's mean the object is the object is 25 degrees Celsius and the environment is 75 degrees Celsius. So there will be an exchange of energy, net rate of energy exchange. So you substitute the formula dq p equals to E Boltzmann constant A T to the power 4 into the equation here. So the power will be PF minus PI. Okay, so use this one. T final minus T initial to the power of 4. Be careful, many students make mistake with the equation here, forgot to put the power 4 here. Okay, so now factor out E, Boltzmann constant and surface area. And in the bracket, TF to the power 4 minus TI to the power 4. Okay, so E is 0.8. Boltzmann constant is 5.67 times 10 to the power of negative 8. And then the surface area is 3 meters squared. Okay, all already in SI unit. And the temperature is convert to Kelvin. So given here in degrees Celsius, so you need to convert to Kelvin. So that 75 degrees plus 273 degrees Celsius, 25 degrees Celsius plus 273 degrees Celsius. So you get in Kelvin. So you get the answer 9.23 times 10 to the power of 2 joule per second. Okay, so this is the net rate of energy exchange of the object. Okay, so rate of energy means power. So net power. Okay, so now for the net energy absorbed, because the surrounding is 75 degrees, so it absorbs the energy. So net energy absorbed. So usually, if the at equilibrium, the heat energy radiated is equals to the net energy absorbed. Heat energy absorbed. Okay, so we can use this power net to get the net energy absorbed. So from P equals to dQ by dt, so the Q will be P times T. So P is 9.23 times 10 to the power of 2 times the 50 second here. So you get the answer 4.62 times 10 to the power of 4 joule. So this is the net energy absorbed. Okay, so next question 4. Then we go to question 5. Question 5. Okay, question 5. Figure below shows a metal rod PQ, okay, of length L, and diameter increases uniformly. So this is a little bit different from the question 4 because the diameter is increases. Diameter increases. So from P to Q. Okay, the rod is well insulated. So ends P and Q are fixed at temperature theta 1 and theta 2. So different temperature, theta 1 larger than theta 2. So that means the heat flow is from P to Q, from hot end to cold end. Remember that the heat flow is from hot end to cold end. So that's in from P to Q. So which of the following graphs shows the variation of temperature theta with distance x from P when a steady state is achieved? So be careful here. Steady state is when the dq by dt or power is constant. So there is the q of dq by dt is constant along the way here, P to Q. Okay, so that's mean with the formula we use is dq by dt equals to negative ka d theta by dx from Fourier's law. So this is from Fourier's law actually. Okay, you are given the x is length L and the diameter to relate with surface area. So you can use the cross-sectional area here as pi r squared, which because of diameter, so you convert to pi d squared over 4 because radius is diameter over 2. So it's become pi d squared over 4. You can relate with area here. Okay, then theta 1, theta 2, the change in temperature, then steady state. Steady state. So dq by dt is constant. Okay, and then A is not constant, so A increases. So if A increases, K is constant because it's the same rod. Okay, same metal rod. So K is constant. So the changes is A decreasing, A increasing, sorry, because diameter increases. So A increasing. So what happened to the temperature gradient? This is called temperature gradient, d theta by dx. So that means temperature gradient decreases. So from the graph here, so which shows the graph for gradient decreasing, and gradient decreasing. So that means the answer is B. So decreasing. The gradient at the top here, we choose one point at the top here, so it's larger than the bottom here. The bottom here, the gradient is lower compared to the top one. So that means the temperature gradient decreasing. Okay. So the answer is B. For A, it's no, because the gradient is constant. Temperature gradient is constant. You see, the gradient is constant, so temperature gradient d theta by dx is constant. Whereas from the relationship here, it's supposed to be decreasing. So A is not the answer. C is increasing. The gradient is increasing. D is not the answer because here become constant. So the correct answer is B. So very simple. And then we go to question 6. Question 6. Okay, the diagram below shows a uniform rod of length X and cross-sectional area A, which is perfectly insulated. So the two ends of the rod are maintained at temperature θ1 and θ2. So θ1 larger than θ2. So again here, which one is a hot end? So θ1 is hot end, θ2 is cold. So the heat flow will be to the right, from θ1 to θ2. Okay, so the same material is used. So what does this mean? The K is constant. Okay, which of the following setups will produce the same rate of flow of heat as the above setup? So dQ by dt, the rate of heat flow is dQ by dt. So from the formula, Furer's law, dQ by dt equals to negative Ka d theta by dx. Okay, so you substitute all the given data here, information given. So it's x, okay, dx is x, there x. Okay, θ2 minus θ1, and k is a k for this rod. Okay, A. Okay, A is given here. This is A, given. Okay, so everything is given. You use that symbol given in the question. Don't use other symbol. Whatever given here, you write down in the substitute into the equation. So this one keep for a while. Then you look at the answer A, B, C, D. So for question A, the length become half, temperature become half, both end. B, temperature become half, but the length constant. The cross-sectional area become half also. For C, the cross-sectional area is double. Look at how thick the rod is. They become double. Temperature remain the same. Temperature remain the same. And this one, cross-sectional area remain the same, but temperature half. Length remain the same. X. Okay, so which one will give the same dq by dt? So that means you need to use use the equation here one by one. Okay, let's start with A. So dq by dt equals to negative. K is a rod, same rod, so K remain the same. A is a rod of cross-sectional area A, so you substitute A, the same A. And then temperature, temperature half θ2, this one half θ1. So half θ2 minus half θ1. So negative cancel out, become positive. And the distance here half x, so you substitute half x. Then you simplify, factor out half, and you get, what you get? So negative Ka θ2 minus θ1 per x. And compare these two. Okay, so you get same answer. So no need for us to do for question B, C, and D. Because we found the answer already. The questions one, which one produce the same rate of heat flow. So that means A is the answer already, because you compare these two, answer they are the same. But for exercise, you can also do for B, C, and D using the same equation, and you will find out that they are not the same. That one you can do by yourself. Okay. So now we do A already, so we get the same answer. So the answer is A. Okay. Okay, now I give you extra question actually. The question I give you is six, but I have seven, question seven, where the changes now from the previous law. Okay, the changes here can be what we do just now is between A between A and K, or between A and temperature gradient, and sometimes between dq and dt by K. So it depends on the question. So let's do question 7. What are the change now? The change now is by the K actually, the K, because different material we use, glass, air and glass. Let's read the question first. So the diagram below shows the twin walls of a room consisting of layer of air in between two identical layers of glass. The outside temperature is 30 degrees Celsius, while the temperature in the room is 20 degrees Celsius. Okay, so this is outside temperature 30 degrees Celsius. So this is the glass, and in between got air, and this is room, inside the room 20 degrees Celsius. So by assuming that the transfer of heat is steady state, so that's mean the rate of heat flow is the same, because mentioned here steady state. Okay, by conduction, so which of the graph shown the variation of temperature across the twin walls? Okay, so from the equation of Pierce's law here, so that means steady state dq by dt is constant. Okay, K will be different. A is constant because it's a window. It's a window. So the surface of the window is the same. So A is constant. So the changes now is between K and temperature gradient. Okay. So for A, because the glass here, this is glass, so that's mean automatically in your mind, that's mean the gradient will be the same. D theta by dx is temperature gradient, so the gradient of these two must be the same. So you can see that the answer is A already. This one, for question B, the gradient is not the same. Look at the first and the last gradient. This one also not same, and question answer D also not same. So look at A, the gradient is the same. So you can guess the answer already. Okay, glass, same gradient, temperature gradient, d theta by dx. Okay, then for the air, compare with air and glass, K thermal conductivity, K is thermal conductivity. Thermal conductivity for A is less than thermal conductivity for glass. So that's mean temperature gradient is temperature gradient is inversely to K. Look at K and d theta here is in the same side. So that's mean they are inversely to each other. So if K air is less, so that's mean temperature gradient will be larger. Look at the gradient there, larger than the glass. Okay, so larger gradient, shown by the larger gradient. So that's mean the answer A is the correct answer. Okay, so this is extra question for you all. So now we've come to the end. Okay, and with God grace, we have reached the end of today's lesson. Okay, congratulations to those who are able to follow our lesson from the beginning till the end. And so all of you, please stop posting your comments for a while. Okay. And click the subscribe button and activate the icon bell so that you will not miss the next class lesson. Okay, then if you find that the lesson was beneficial, click like and share to your friends on your social media. Spread and share the goodness. Once completed, type done on the chat box before the certificate link is given as a token of thank you for your dedication in joining the free online class today. So I will put the link now, okay, for the certificate. Okay, I paste it in the chat box. Okay. So posted there already. So please take note, the link end half an hour after this live, and make sure to use the EDD email and MOE email only to log in. Okay. So if you haven't got one, please apply. The link to apply the EDD email is already given in the chat box. You can scroll up there. And if you wish to get more information on the online classes, so you go to www.academyyoutuber.com. And to those who haven't joined Didik Dunia Telegram, so please do so. So once again, I would like to thank all of the students for joining today. You are awesome. And feel free to share this free tuition class to your friends and teachers all over Malaysia. So this is the collective effort actually from all the teachers throughout Malaysia for all the students throughout the country. So thank you too for being a YouTuber Academy supporter too. So I think that's all for now. So see you in another lesson. So remember with the hashtag bermula percuma and selama percuma. So initially free and forever free. Assalamualaikum and stay safe till we meet again next week, same day, same time on Sunday at 5 p.m. Okay, bye-bye.